Okay, so in this video I'm going to talk about how we can avoid the large round-off errors that happen in Gaussian elimination, or can happen in Gaussian elimination. So these errors, as I showed in the last video, can occur when you have a large multiplier that ends up being subtracted from a relatively small number while doing Gaussian elimination in a row. So how can we avoid this? Well, we can avoid large multipliers by making sure that we don't need to divide, when we calculate our multipliers, we don't divide by a very small number. And so what we're going to do is we're going to pivot or reorder the rows below our pivot point so that the largest value is the pivot. Okay? And so we can write this as saying, all right, we want AII, our pivot point, to always be greater than all the sorry, I've got those backwards, all of the entries that are underneath it. So that's going to be from the j's that are from I, the pivot point, to the end of the matrix. So again, if we are looking at our matrix and we have AII, then this is going to be I plus 1 I, A all the way to A J I, A N I. And then the rest of the matrix will still be filled in. So essentially what we're going to do is say, okay, we want to guarantee that this value, the pivot point, AII, is larger than all of the rest of them. Because this is going to guarantee that our multiplier, which would be calculated as AJI over AII, since we're trying to guarantee that AII is always bigger than AJI, this will always be greater than or equal, or sorry, this will always be less than 1 for all of the multipliers that we have to calculate to perform the Gaussian elimination. Okay. So what does this look like in practice? Well, if we go back to our example, we had 10 to the negative fifth, 3, 2, 1. And if we look at this, well, we want to zero this out, but if we do our check, is AII greater than AJI? Well, AII is this 10 to the negative fifth, and it's most definitely not greater than 2. So what we're going to do is we're going to exchange rows 1 and rows 2. And when we do that, we're going to exchange the whole row. So we have 2, 1, 10 to the negative fifth, and 3. And remember, if we're solving a set of equations, we haven't altered the set of equations as long as we also change, for example, our b vector. So if this was to solve a system of linear equations, you would want to change the rows of the entire augmented matrix, not just the A part. Okay, so we switch our rows, and now we can do very similar to the operation we did before. We're going to take row 2, and we're going to set it equal to row 2 minus our multiplier times row 1. But this time, rather than our multiplier being 2 divided by 10 to the negative fifth, which was a really large number, we have 10 to the negative fifth divided by 2, which is a very small number. And so this is going to end up being 2, 1, because that row's not changing. 10 to the fifth, negative fifth divided by, or 10 to the negative fifth minus 10 to the negative fifth divided by 2 is going to end up being 0 as designed. And then for the last entry, we're going to have 3 minus 10 to the negative 5th times 1 divided by 2. And we're going to go ahead and say, okay, remember we were operating in 3-digit precision, so this is actually going to just be 3 minus a very little bit, which will end up rounding off. So this includes the rounding in 3-digit. But unlike the case we had before, where when we rounded off, we ended up rounding up and thereby drastically altering the value of that entry by a whole 1, in this case, we're rounding down, and it's only by a very little bit, something around the size of 10 to the negative 5th. So in this case, when we now go back and do our check what is L times U, so now this is our U, and our L, let me just write it here, our L ends up being, again, 1, 0, 1, but with the multiplier, which this time was 10 to the negative 5th divided by 2. So if I take this L and multiply by my U matrix, we end up getting 2, 1, 10 to the negative 5th, 3, which is which is the same as our original matrix when we swapped the rows. So LU is not equal to A until we account for pivoting. And we can do that by multiplying this by a P matrix that accounts for this switch. So I will show you in the next little video, basically we still need to swap the rows to get A back. So in the next video I'll show you the rules for how to design a P.